Hello everyone, welcome all to the GATE solution series. So in this video we are going to discuss some questions from real analysis from GATE 2021 paper mathematics. So let's get started. So the question number 11 is on your screen. So in the question number 11 we have to check the validity of the two statements P and Q. So we will start by first defining what do you mean by metric on a set. A metric D on a particular set A is actually a function from A cross A to R. It's in fact it's generalization of distance. So with satisfies some certain properties. First property is distance between any two points x, y is always non-negative and is 0 if and only if x equals y. The second point is distance between x, y must be same as distance between y, x. Right? And the third is triangle inequality. Distance between x, z is equal to is less equal distance between x, y plus distance between y, z for any point x, y and z belong to the set A. So these are the properties which must be satisfied by a function D, which in order to be a metric on a particular set A. Okay. So according to these three properties, we will verify whether the D1 and D2 satisfy these properties or not. Okay. So let's start with D1. Okay. So what is D1? D1 is log of x by y, modulus of log x by y. Okay. So D1 is defined as D1 at point x, y is defined as modulus of log x upon y. Because y is non-zero, because A is the set open 0, 1, y never becomes 0, so this function is well defined. Also x by y is always positive because x is positive, y is positive. So log is well defined, hence the function, this function is well defined. Okay. Now, because modulus value, by taking the modulus value, we already satisfied the axiom 1, the statement 1, that is the distance must be a non-negative value. So we have satisfied the number 1 property, and distance between x by y. Okay, so let's find what is distance between y by x now. Distance between y by x is equal to modulus of log y by x, right? But we know this is equal to modulus of log of y minus log of x, which is same as, because it's modulus, I can just take minus and common, and in the modulus it will again be the same value. So it is same as log x minus log y, which is again same as modulus of log of x upon y, which is equal to distance between x and y. So the second property is also satisfied. Let's check the third property. The main property is the triangle inequality, which is the third property always in any matrix. The first and second property will be certain mostly. So let's check the third property. Okay. So what we have to prove is distance between x, z is less equal distance between x, y plus distance between y, z for any arbitrary x, y, z. This is what we have to prove. Okay. So let's think, how can we do this? Okay, so let's start with distance between x, z. Distance between x, z is what? Modulus of log, log x by z. So I can write as modulus of log of x by y into y by z. I can write like this because y is any positive number, lies from 0 to 1. So I can write like this, which is same by using modulus property. This is log of x by y plus log of y by z, right? Now by the triangle inequality in real numbers, because log of x by y is a real number now A, suppose, and y by z is real number A. So modulus of A plus B is, I know, less equal mod A plus mod B, which is modulus of log x by y plus modulus of log y by z. What is this? This is D1 at x, y plus this is D1 at y, z. Oh, sorry, I mentioned this is all D1. We are talking about D1 right now. So what I got is d1 at x comma z, this is less equal d1 at x comma y plus d1 at y comma z for any arbitrary x, y, z. So I am done. All the three properties are satisfied. So this d1 is a metric. Right? This d1 is a metric on open 0, 1. So P statement P is correct. Now similarly, let's check for the statement Q. In statement Q, the metric d2 is defined as d2 at any point x comma y is equal to, okay, we just watch it here, is mod x plus mod y where x is not equal to y and 0 when x is equal to y. Okay, so there is no point of taking modulus here because both x and y are positive because those belongs to open 0, 1. So I can straight away write like d2 at x comma y is x plus y when x is not equal to y and 0 when x equals 0. Okay, so first property, see x and y are both positive, so their sum is also always positive, so it can't be negative always. So first property is straight away satisfied. And distance between any 2 points is 0. Distance between x comma y is 0. What does imply? Okay, suppose x and y are not equal, then what can happen? It will be x plus y, right? But because both x and y are positive number, strictly positive number, so their sum cannot be 0, right? Their sum cannot be 0 because the sum of two positive numbers is again strictly positive. So this can't happen. So x and y must be same, and this is the only case where the distance is 0. So that's trivial. Okay, the first property is satisfied. Similarly, you can straight away say distance between y comma x is same as distance between x comma y. When they are not equal, they are just sum of these two numbers. So addition is commutative, so you can straight away see it's equal to distance between x comma y. So second property is also satisfied. So let's look at the third property. We have to prove distance between x comma z is less equal distance between x comma y plus distance between y comma z, right, for any arbitrary x, y, z. Okay, so let's think how can we do this. Okay, let's start with the right hand side now. What is d2 at x comma y plus d2 at y comma z? d2 at x comma y is x plus y. Okay, I am assuming all these are different. Okay, x plus y plus d2 at y comma z is y plus z, right? I am assuming case 1. Okay, I will make some cases. Case 1, x is not equal to y is not equal to z, right? Okay, so now this is equal to x plus 2 times y plus z. But you know y is positive, so 2 times y is a non-negative, is some positive quantity, right? So this sum is always greater or equal x plus z because 2 times y is some non-zero positive quantity. So this inequality follows. But what is this? This is simply d2 at x comma z. So I got this, that d2 at x comma z is less equal d2 at x comma y plus d2 at y comma z. Pretty simple, no? So in first case I got it. In second case, it's just one of these may equal, like suppose x is equal to y or y equal to z. But in that case, you can straight away think either this will be 0 or this will be 0. Okay, suppose without loss of generality, suppose x equals y, then what is d2 at x comma y plus d2 at y comma z? This is if x is equals to y, this is equal to 0 plus d2 at, because x is equal to y, this is same as d2 at x comma z, which is, I mean, there is nothing, like this follows in the inequality sign. d2 at x comma z, I can still write d2 at x comma z is less equal d2 at x comma y plus d2 at y comma z. In this case, it will be just equal. So in both the cases, the inequality follows. So both d1 and d2 satisfies all the three properties of being a metric. So both p and q statements are correct. So answer to this question is A. Both p and q are true. Right? So let's move on to the next question, which is question number 12. Okay, So what is given in the question is f be a function y is continuously differentiable with some properties, and s be a surface, like it is a sphere in R3, n cap be the outward unit normal to s, and we have to evaluate this integral, double integral over s grad f dot n cap ds. Okay, so for this we need Gauss divergence theorem. I will tell what is a Gauss divergence theorem. Gauss divergence theorem. Then what Gauss divergence theorem says is double integral over s f dot n cap ds is same as triple integral over d divergence of f dv. Right? I mean, it straight away converts a surface integral to volume integral, right? So this question is very straight away right now, because we know here f is what? F is gradient of f, because f, small f is a scalar function given with twice continuously differentiable, right? So we can again differentiate grad f to obtain its divergence, and it satisfies all the conditions in the Gauss divergence theorem. So we can apply Gauss divergence theorem, and straight away double integral over s grad f dot n cap ds will be same as triple integral over d is the region in the surface, divergence of gradient of f, right? Divergence of grad f dv. Okay. So we have given what is divergence of grad f. Divergence of grad f is 6. It's simply, it is triple integral over d 6 times dv, which is 6 times volume of the sphere. Which is equal to 6 times what is volume of the sphere? It is 4 by 3 pi r cube. R is 1 here. So it is just 3 to the 6, it's 8 pi. That's it. I mean, now बताओ कौन बोलता है कि it is very tough? I mean, look at this question, man. So the answer to this question is option number D, which says 8 pi, right? Yeah, 8 pi. Okay, so let's move on to the next question. This is question number 15. Okay. In question number 15, we are given some information related to the partial derivative, so directional derivative of f at point 0, 0 along two different directions u and v, and we need to compute fx at 0, 0 and fy at 0, 0. Okay, and the function f is also differentiable here. Okay. So we need a formula, a sort of formula. Closely look at this formula. This is very important. The directional derivative of function f at point, suppose a comma b. Okay, here I write a b for simplicity. F at a point a b in the direction of u bar is given by simply gradient of f at point a comma b dot product u cap. Where what is u cap? U cap is a unit vector along the direction of u bar, which is simply u bar upon its magnitude. Okay, so just we will use this formula and we'll get to the answer. Okay, let's assume, okay, what is gradient of f? Gradient of f is simply fx at point given point, suppose 0, 0, I write grad f at 0, 0 I cap plus fy at 0, 0 j cap. So this is gradient of f at 0, 0. Okay, I will just name this term as ai cap plus fy at b, just renaming. Okay, so gradient of f at 0, 0 is ai cap plus bj cap. So basically what I want is a plus b. Yeah, I want this. So let's use the given sum, and see, already these two vectors are unit vectors, because what is norm magnitude of u, which is square root of 1 by 5 plus 4 by 5, which is 5 by 5, which is 1. Similarly, no, magnitude of v is also 1. So gradient of f we just have to find now. Gradient of f is Okay, gradient of f you don't have to find. This is unknown, ai cap plus bj cap. So what is grad f dot u cap? Is dot product of this, which is a by root phi plus 2b by root phi, which is given as root phi, right? Which implies a plus 2b is equal to phi. Similarly, grad f dot v cap, which is equal to a minus b upon root phi, which is given as root 2. Right. So this is root 2, which implies a minus b equals to 2. Now we just have to solve these two linear equations, and by solving these two linear equations, what we get is, okay, this plus 2 times this, so 3 times a equal to 5 plus 4, that is 9, which implies a equals to 3, and substitute a in this equation, so you just get b equals to 1. So we got a is 3, b is 1, so a plus b is what we needed, right? A plus b will be 4 then. So right, this question is sorted. Let's move on to the next question. Question number 16. Okay. Let gamma denote the boundary of the square region R with vertices 0, 0, 2, 0, 2, 2, 0, 2 oriented in the counterclockwise direction. Then we have to find this line integral, sort of. Okay, so let's draw the boundary gamma. What is it? Is just this point 0, 0, this square 2, 0, 2, 2. Okay, this is not well shaped, but okay, 0, 2. This is the square and anti-clockwise direction. This is our boundary. Gamma, we have to integrate, we have to find this. Right. So we'll use the Green's theorem here. Green's theorem says it just converts this green line integral over suppose gamma m dx plus n dy will be equal to double integral da by n by da by x minus da by m by da by y dx dy over the region A. Suppose what is A? If gamma is this boundary, then A is the region enclosed by this boundary. Okay? But the conditions here were m and n must have continuous first order partial derivatives. This is the condition for Green's theorem, and here because our m and n, this is m and this is n here, and dx plus n dy, and both of these have continuous first order partial derivatives, so we can use the Green's theorem here proudly. Okay, so let's just now what is, first of all, A is this region, this square region. So this integral, what we have to find is just equal to double integral. If I just put the values of this region, then x goes to 0 to 2, y also goes to 0 to 2, and da by n by da by x is 1, minus da by n by da by y 0 minus 2y, so minus minus plus 2 times y, this is dy dx, which is equal to integration x goes from 0 to 2 respect to y, which is y, plus y squared from 0 to 2 dx, which is equal to with respect to x it is just 2, and if you put the value it is 2 plus 2 square is 4, so it is 4 plus 2 6, 6 to the 12, so the answer is 12. See, such easy questions are there in GATE. People say GATE is very tough. You just have to do the hunting of easy questions. There are a lot of easy questions in GATE examination. There are tough questions. I don't say that like GATE is very bacha thing, but you have to do the hunting of easy questions. There are always easy questions. So okay, so let's move on to the next question. Question number 37. So it's a big question, right? But the 37th question says is they have given a function and we have to check the validity of the two statements P and Q. Check करना है whether f is okay. So one by one we will look at the statements. The first statement P states that f is continuous at 0, 0, but f is not differentiable at 0, 0. Okay, let's check. Okay. But to check continuity, we also know another definition. Like at 0, 0, we have to just check limit. Right, we have to check the limit as xy goes to 0, 0, f of xy, correct? But this is same as limit as r goes to 0 from positive side, f at r cos theta, r sin theta. We'll check if it is equal to 0, then we are through. In fact, this is because the point 0, 0 is there, right? In general, we put x as a plus r cos theta and y as a plus r sin theta. Sorry, not a, b plus r sin theta, where the point to check the limit is a comma b. This is in normal substitution to use this kind of limits. Here, because a b is 0, 0, we just straight away put x equal r cos theta, y equal to r sin theta. Okay, so let's check this limit. What is this limit? Limit as r goes to 0 positive. This quantity will be just r square root of r square is r into sine of y square by x, which is r square sine square theta upon r cos theta, which is this thing. And you know this is bounded and this goes to 0, so overall limit goes to 0. So the limit of function as xy goes to 0, 0 is 0, which is same as the value of the function as x comma y equal to 0. So the function is continuous at 0, 0, right? Now we'll check whether the function is differentiable or not. Okay. The sufficient condition for the function to be differentiable, okay, is like the function must have, the function should be expressed as this f of h comma k minus f at 0 comma 0 must be equal to square root of h square plus k square into some function of h comma k plus ah plus bk, where a is fx at 0, 0, b is fy at 0, 0, and limit as h comma k goes to 0, 0, phi of hk must be equal to 0. So let's check if this thing happens. Before this thing, we have to first check whether the partial derivatives exist or not. If they doesn't exist at the first place, the function is not differentiable. So let's check what is fx at 0, 0. This is limit as h tends to 0, f of h comma 0 minus f of 0 comma 0 upon h. What is this? This is limit as h goes to 0, f of h comma 0 is square root of h square. Okay, so f of h comma 0, which implies y coordinate is 0. So this is 0, so sine 0 is straight away 0. So you just got 0 here. 0 minus this is 0. So it's just 0. And fy at 0 comma 0, which is equal to limit as k tends to 0, f at 0 comma k minus f at 0 comma 0 by h. But what is f at 0 comma k? By definition of the function, whenever x coordinate is 0, the function is 0. So it is also just 0 minus 0, which is 0. So both the partial derivatives exist and all 0. So here this expression will just reduce to, this thing cancels out because a and b are 0. This thing cancels out. This is just this. So let's check now this thing, whether this thing happens or not. k. What is f of h comma k minus f of 0 comma 0, which is equal to square root of h square plus k square times sine of k square by h, if I am not wrong to remember the question. Sine of square root of h square plus k square sine of k square by h, correct. Minus f of 0 0 is by definition 0. So we are sort of in this form, right? Square root of h square plus k square into this is phi of hk. But does phi of hk goes to 0 0 as hk goes to 0 0? So let's check. We have to check now the limit of the limit as h comma k goes to 0 comma 0 to this function sine of k square by h. But if the limit exists, then the limit in along every path must be same, right? If you go along the path k equals 0, then the limit is equal to 0, right? Sine of 0 equals 0. If you go along the path along h equals k square, right? This also path is valid. Along this path, the limit will be what? Limit will be equal to sine of simply k square by k square, right? Which is 1. So this is the limit. If you go along this path, so along different path, limits is different. So this limit does not exist. Not even this limit does not exist. So the function is not differentiable. Okay. So P statement is correct. Now you have to check whether the Q statement is correct or not. Okay. I think I need the question again here. Okay, so now to check whether the directional derivatives of f at 0 0 along any direction u exist or not. What are the directional derivatives definition? If u, everything you just sort of first go to the definitions. I mean, most of the things are done by the definition. If u is u1 I cap plus u2 j cap, and we have to check the directional derivatives at point x0 comma y0. Suppose the directional derivatives, suppose I write like this: du of f at point x0 comma y0 is just limit as h goes to 0 f at x0 plus h u1 comma y0 plus h u2 minus f at x0 comma y0 divided by h. Okay, so this is the definition. So now if you want to check at point 0 comma 0, it is just du at f comma 0 comma 0, which is equal to limit at h goes to 0 f at h u1, right? h u1 comma h u2 minus f at 0 0 is 0 straight away divided by h, which is equal to limit at h goes to 0 h u1 h u2. It will be square root of h square u1 square plus h square u2 square. So simply it is square root of h square into u1 square plus u2 square into sine of y square, which is h square u2 square divided by h u1 divided by h, which is equal to limit as h goes to 0. This is h square root of u1 square plus u2 square into sine of h u2 square upon u1 whole divided by h. This h will get cancelled. This is a constant quantity. see here, this is also a constant quantity, and limit as h goes to 0, this term will goes to 0, sine of 0 is 0, so this limit is 0. Okay, is there something wrong? Yeah, cool. The directional derivative at every directional derivative at 0 0 along every direction u exists and is 0 in fact. So both P and Q statements are correct. So the correct option to this question is option number A. Okay, so let's move on to the next question. That's probably the last question. Yeah. Okay. So this is pretty simple question, the 39. Though we have to find the critical points first, and we have to classify the critical points along the, like saddle point or maximum or minimum. The first thing is the critical points of f are the solutions to the equation fx equals to 0 and fy equals to 0, right? Let's find this. What is fx? Fx equals to 4 times y minus 4 times x, which is equal to 0, which implies simply y equals to x. Equation number 1. What is fy? Fy is equal to 4x minus 4y cube, which is equal to 0, which implies x equals to y cube. Equation number 2. From 1 and 2 we got y equals y cube, which implies y times 1 minus y squared is 0, which implies y equals to 0 and y equals to plus minus 1. So the critical points are 0, 0, 1, 1, minus 1, minus 1, because x equals y is the solution. Okay, so let's check now the critical points. We have the critical points, and to classify the points and in these conditions, like maximum, minimum or saddle points, we have the conditions. Like we have to find what is d. D is the discriminant, which is fxx at, we are now, this is to be considered as to check at critical points. Fxx at point, critical point AB, fxy, fyx and fyy. In particular, this fxy and fyx must be same always, so this is straight away fxx into fyy minus fxy squared. This is value of d. So the first condition is, if d is positive and fxx is negative, that it will give you the maxima. Secondly, if d is positive and fxx is also positive, then it will give me the minima. Third condition, if d is negative, it is saddle point. Saddle. Now if you observe, what is fxx? Fx is 4y minus 4x, so fxx is just minus 4y. So for any point, fxx must be always negative, so we'll either get maximum or a saddle point, right? So we'll check the value of d at these points. So what is d? Okay, so fxx we know. What is fxy? Fxy is, I guess, 4, and fyx. Fxy is 4. Fyx is also 4, which must be same as I said. And fyy. Okay, I think I should cut some of these things. Fyy is minus 12y square. What is the value of d, which is equal to fxx minus fxx into fyy, which is 48y square minus fxy squared, it's 16. Right. Okay. So at point 0, 0, what we got, t is minus 16, right? It is negative, which implies saddle point, one saddle point we got. And d at any other, like 1 1, you get 48 minus 16, which is positive, and f(x) is straight away negative, so you got a maxima, right? So each option is correct. A point of local maxima and a saddle point, right? 13. A option is the correct option. So that's it. So I think we have finished. Yeah, so these are the questions from real analysis section. As you can see, there were not too tough questions. All the questions were easily doable. You just have to hunt for the easy questions and you are through. So hope you like the video. So that's it. We'll meet in the next video. Bye bye.